Right. So, hello everyone. Today we have with us Jonathon Luiten. He's a PhD student at RWTH, Aachen University. He's also a research visitor at University of Oxford. Today we are going to discuss his paper on Siam R-CNN, and let's hear more about him from Jonathon. Please go ahead.
Cool, thank you very much. So today, Siam R-CNN, visual tracking by redetection. So this was a paper that we presented at CVPR 2020 with my colleague Paul and our supervisor at the RWTH Aachen, Bastian Leiber. And I did this work while I was on a research visit last year to the University of Oxford with Professor Philip Tor. So let's begin. So first, a bit of a pixelated image there. What is visual object tracking? So basically the task is that we're given a template. So usually this is in the first frame of the video. And in this case, it's a bounding box patch. So you're given in one of these frames, this bounding box of a region to be tracked. In this case, it's the head of a person. And then you want to track this throughout the whole video. So you can see a pretty fun video here with some results of our method that work pretty well. So that's the task that we're trying to solve. So there's a number of different versions of this that we're going to look at here. So short-term tracking, typically videos are short, but still can be long, but the object is usually present in every frame. This contrasts to long-term tracking, which you can see here where the object disappears, and then you have to re-find it and track it again after reappearance. And usually in this case, the videos are much longer. And then also video object segmentation, which is exactly the same scenario, except that the initial templates to track are given as segmentation masks, and the required output of tracking is also segmentation masks. And in this case, you can also see that sometimes in one video, multiple objects need to be tracked, so multiple templates are given simultaneously. So what have been previous approaches to solving these kind of things? So research on this goes back as far as 1981. So famous computer vision method, Lucas Canade tracker. So this was originally proposed for optical flow. And basically, it then can be easily generalized to tracking. So in optical flow, basically what we want to do is we want to track a single pixel and how this moves throughout the image. But there's no reason why exactly the same kind of idea can't be extended to larger patches, e.g. whole objects, and track how these move. So one simple way to kind of explain this idea is, so we have this equation here, this energy function, and we can evaluate this. And so we have an image, so current frame, that we're trying to find the object, and a template, so that's, say, the object in the first frame, what we're given, what we're trying to track. And so one way to do this is to simply take this template model, correlate it across different positions on the image, so in a sliding window approach. So take this template, compare it to different patches in an image, and then see how, in this case, how the intensity, so the image pixel colors of the patch compared to the template. And then when you do that, hopefully, if everything's easy and well, it compares highest where the actual object is, and you get tracking. So this was how these things worked, and back in the 80s. This was already working okay, I guess, like some cases, but doesn't always work. And one of the problems is that objects change their appearance over time. So if you're searching this template over new images, well, the object's going to change, and you're not going to necessarily find the correct object, as you can see with this car. So one of the solutions, maybe not the only solution, is to not directly compare pixels, but instead compute features over these pixels, which are hopefully invariant to such changes, such that when searching in a, say, sliding window correlation approach over the image, when comparing the features of the target image to the features of the template, you still are able to match to the correct object, even when the object appearance changes. So this worked much better with, like, once we got into the mid 2000s, when we got features like SIFT and HOG, highly traditional engineered features, but these worked really well compared to what was before that. And so that was state-of-the-art tracking at the time. So kind of correlation-based, template-based tracking. So then you know, when deep learning came about, it makes sense to use deep features for this task. So one of the first methods that did this, the Siam FC. So basically the idea is, when we look back at it now, it seems very simple. So basically you just extract deep features. So you can see in this diagram that they have a feature extractor, and this feature extractor is what we call Siamese. So what this means is that the feature extractor is shared between the image and the template. So both of these are extracted with fully convolutional network, such that you get a deep feature representation for the template and a deep feature representation for different patches in the image in a fully convolutional way. And you can simply then convolve again this vector with this representation and calculate the similarity. So this convolution operation is the same as what's in a typical convolutional network, and it's equivalent to like a sliding window approach or just a correlation analysis. And that gives you a heat map of these correlation results for where it's most likely that this template is going to be present. And so when this came about, deep learning, we all know the success of deep learning. Things worked really well, so results improved dramatically. So the next big thing that happened with tracking is basically the way I see it is that tracking was improved by using ideas from object detection. And so one of the main papers here is the Siam RPN, so Siamese Region Proposal Networks. So instead of just basically doing this sliding window approach on the features, what they do now is they use the successful ideas from object detection that people have developed over the years. So in this case, they take a bunch of proposals and they basically have two heads of their network. So one classifies each proposal as to whether or not it's likely to be the template object. And the second one regresses an offset for that proposed box. So in this diagram, basically you have, similar to the last one, you have CNNs that encode both the template and the frame. And then instead of having just a single correlation, you learn some different features, one for classification, one for regression. You do that correlation to get some correlated features, and then you output in this case, a logit for whether it's the same or not, and in this case, regressed values for how you want to change that bounding box so that it best fits the object. And so again, as we go through time, these methods get better, and this helped a lot. So this approach worked really well, and in fact, up until I guess we presented this paper, this kind of approach was the state of the art for tracking. So before we published our method, the previous state of the art was called Siam RPN++. So more modern advancement of what I just showed you, and it's basically, I mean, I'm simplifying it a lot, but it's basically just the Siam RPN method with deeper networks and well-tuned architecture. Obviously, there's more to it, but basically that's the approach. So basically, when we started this project, we saw this as the state of the art, and we'd also been doing some work in object detection. And basically, if you look at the way that I've explained it so far, you can see that there's some potential for using the ideas from object detection that have been shown to work really well in object detection to improve tracking. So let's have a little look at what these advances in object detection over time are. So basically, object detection methods, again, I'm simplifying, can be divided into two kinds. So single stage methods and two stage methods. So single stage methods work using basically this region proposal network, the same as what we talked about just before. And so a good example of this is the RET-IN-A-NET method. So it still works well, but it works less well than two stage methods, but is usually much faster. So in contrast, two-stage methods, typical example is faster RCNN or mask RCNN. They basically do the same thing as these single-stage methods. They take these RPNs to generate proposals, but then in a second stage, they take these proposals, they take the features of this proposal. So you already have kind of a proposal for what the box is. They align it to a constant size. So this uses ROI align. It's region of interest alignment. So they get a feature map that's constant size, and a second network head, so a second part of the neural network, takes these features, processes them, and then is able to, at a second stage, output a more accurate classification and regression on these features. So in general, this two-stage approach works much better. And there's been a number of other advances that have shown improved results. So so things that we're going to exploit in our method, so we're going to talk about them. So one is feature pyramid networks. So basically, your deep backbone, instead of just outputting a single set of features for an image, it outputs features on multiple scales, and each of these scales have the context of the other scale. And then when they're used with, say, the fast RCNN architecture, then you can take features from different scales depending on the size of your proposed objects. And then finally, the cascade RCNN architecture, which basically is the second stage of detection that we talked about. If you run this multiple times, so each time it does a regression as well as a classification, so it actually changes the bounding box, it regresses to a better bounding box. And so basically this cascade RCNN just runs this multiple times, each time on the new, most up-to-date bounding box, and then improves the detection by doing this over and over again. So kind of an iterative process. So then how can we kind of use these advances in detection to improve over state-of-the-art tracking? So let's have a look at the architecture that we proposed. So at the start, so this is my diagram. Apologize for the complexity of this diagram. I've been told it's quite complex, but that's why we're going to go through it quite slowly. So what I'm showing you is a diagram just for faster RCNN. So just detection, no tracking yet. So we have a current frame, a deep feature extractor. I've made my deep features all colorful. You have a region proposal network, which proposes regions. So you can see those are boxes. So in here we have multi-scale features. It's hidden in the architecture, but they're there. Propose some boxes in the image. So you align those boxes. So basically you crop the features out of the feature for the whole image to have features per proposal, and then run those through a detection head, which outputs both a classification score here in numbers for how likely that is to be a certain class of object, and also regresses. So I've tried to show a regression here, regresses a bounding box. So then when you add cascade, so I'm just building this up slowly, basically what you get is after you get these ROI aligned features, feed them through the detection head as we did and get a score, you then take those new boxes back and adjust where the boxes are such that you get new features and run it again. So in this case, Cascade RCNN does it 3 times, and we adopt the architecture, so we also do it 3 times. So now, basically, what do? Well, we convert this architecture, this current state-of-the-art detection architecture into a tracking architecture. So we convert this Cascade RCNN into a Siamese RCNN, Siam R-CNN. So from a detector to a Siamese redetector. So what changes? Well, this part all stays the same. We still extract the features. We have a region proposal network, but instead of a detection head, a second stage detection head, we have now what we call a redetection head. So basically, again, like we talked about before, we have a Siamese feature extractor. In this case, we don't extract the features for the patch by itself, but we actually extract the features for the whole image so that it's exactly the same processing as it's done for the current frame. And then we do ROI align on the template patch. So we get exactly the same features as we have in the current frame from the RPN. And then instead of just outputting these features into the head, we actually concatenate the current proposal features with the template features. And once those are concatenated together, we then feed this into a redetection head. And so for normal detection, it outputs a score of how likely this is to be a certain class. So how likely it is to be a car or not a car. In this case, it's classifying how likely it is to be the same or not the same. So we train it such that it should output A, the classification score for if it's the same object or not, and B, also the regression to regress the box of the correct object in the target in the current frame. So again, we have a 3 times cascade. So basically this means that the proposal is able to move quite a lot over three times regression to fit correctly to the correct object. So
yeah, Jonathan, maybe a lot was covered in this slide. We can just ask the audience if they have any questions. Yeah, you can just unmute yourself and go ahead if you have any questions in this slide. Does this slow down the process, Jonathan, by any way, because you're doing twice?
So it's no, so it doesn't really take any longer than a detector, because so I guess it does take some longer, but almost none, because you extract these features for the first template frame once, so just the first time, and then you save these features, and then you use them again for every frame. So if you're doing detection in every frame, or you're doing redetection in every frame, the difference is only one frame worth of computation. So if you have a video that's 1,000 frames long, it's insignificantly longer, and otherwise it's exactly the same as the detection architecture. So obviously the two-stage architecture is slower than the one-stage architecture, the same as for detection. But this architecture is no slower than the detection version of it.
Understood. Yeah. Yeah, I think you can go ahead. Yeah.
Cool. So how does this compare to the one-stage version for tracking? So Siam RPN versus Siam R-CNN. So what we see is we see a similar improvement as we have seen for detection between single-stage and two-stage architectures. So two-stage architecture makes sense, it works better, it's more powerful. Also, we get a really nice property that because we take these multi-scale features and we crop them all to the same scale before comparing them, then we can naturally deal with changes in object scale over the video, because you're always comparing things that are aligned to be the object bounding box size. This is a nice natural thing that you don't get with other architectures. Another thing is, which is especially important for long-term tracking, is that we do redetection over the whole image. So we take the whole image in, we get the region proposals for the whole image. And then in the second stage, we compare how likely they are to be the template object. Whereas previous methods had relied on a strong bias as to the localization of where the object was before, and usually only considered proposals relative to the previous tracking result. So this means that our method is able to easily recover from objects that have gone out of frame and come back, or objects that our thing has just missed in a previous frame. And also means that it's less prone to drifting over time because it has less reliance, and in the default case, no reliance on the previous predictions. It just takes the template and redetects this template. However, there's potentially one downside for the method, and that's that in the way that I presented it, in order to redetect something, it relies on the RPN generating a proposal which is similar enough that it can regress to the correct box. And so if the RPN doesn't generate good enough proposals for the objects, if you want to track something weird that it doesn't think is kind of an object, then this might be a problem. But later on you'll see, and we don't get into it right now, later on you see that we have a good fix for this that really makes this not a problem anymore. So how do we train this thing? So what do we train first? So we basically at the time we took the best detector that we could find. So we want to take the best tracker, so we took the best detector. So at the time this was, we had a ResNet 101 FPN backbone, used group normalization, had cascade. So this was the best, faster RCN detector that we had. So it was trained on COCO, and we took a detector with pre-trained weights, and we didn't actually update the weights of the network. So of the backbone of the featured network or the RPN. So basically we just took the RPN and had it generate proposals based on what it learned pre-trained on COCO, and then we only trained the second stage redetector for tracking. So how did we train it? Well, we just took videos and we just trained it on pairs of two objects in videos. We just randomly selected one as the reference, as the template, and the other one as the target, as the current frame. And it was trained to redetect given whole images, basically to classify in the other one the correct object, classify yes or no. All of the other potential regions in the image are no, and then also obviously to regress to the correct box from those proposals. And we trained it on 4 data sets of videos with tracking results. and yeah, we trained it and then it worked. So
I had one question, Jonathan.
yeah, please.
When you are processing thousands of videos, have you automated the process? Like, do you do it in batches? How does it work?
I mean, it's definitely automated, as in like
Yeah.
we don't do it by hand.
Yeah.
And yes, the training is in. I think actually in this case, the training isn't in batches because the network is so big that basically, so in some ways it's in batches. It takes one image at a time, so one pair of images at a time. So it takes in just the two whole images. However, at the stage where we're training the redetector head, it is in batches because it takes all of the negatives from the image for training. And actually it does it, training does it in both ways to improve efficiency. So it takes in one frame the template, but it also takes in the other frame the template, and then matches it across to say all of the positives and all the negatives. And there's actually multiple positives per frame because there's different proposals that have different overlap. And if the overlap is greater than X, 70%, then it's a positive, which there might be multiple proposals that are.
And do you skip frames as well? Or in a video, do you skip any frames?
Yeah, absolutely. We train on any combination of frames. So it could be the first frame and the last frame. We just sample 2 random frames from a video. So we want this thing to work long term, not just, you know, from one frame to the next contiguous frame, but we actually want it to work over large variations of object appearance. So absolutely.
So, you are able to try it out on different combination of frames because the frames are not really interrelated, right? You don't want to capture the sequence, you just want to capture the occurrence of the object. Am I right?
Yeah, exactly. So in this case, we're not taking anything temporal. We're just taking 2 random frames and we're just trying to redetect the object in a different frame. Exactly. Where maybe the background is completely changed. A person might have turned around and be backwards and look completely different, but it's the same person. And so we want our network to learn what things are the same, even though they change how they look and change how the background is, etc.
So basically,
Go ahead,
the network is learning the region of interest in which we want, correct? We are not doing anything with temporal.
No, so it just takes 2 frames and it just learns from a template in one frame. So a patch of an image in one frame, it tries to find that exact same patch in another frame.
Yeah, that is what, isn't it kind of, that is a region of interest, right? You want to track that region.
Mm-hmm.
Yeah.
So one more thing that I had in my mind was that when we are talking about visual object tracking, we are not necessarily capturing the movement of an object in all the frames. We are not tracking the path. We are just trying to track the occurrence, right? Because what I assumed was we are trying to track the path.
No, we're absolutely trying to track the path. So we're absolutely trying to find exactly where this object is in every frame. So that's why, I mean, the network, basically what happens is these proposals that go in are like localized regions. So somewhere in the actual image, and you want to tell, is this the object or not? But you also want to regress exactly the size and shape of that object. So we do, so we're going to get to it, but we do then some tricks where we take the temporal nature of the video, the fact that we know that this frame is after this frame is after this frame, and improve the model based on temporal consistency. But that's some extension. The basic method is trained just to be able to redetect something in any frame.
Thank you.
No worries. Okay, let's continue. So extensions. Now the oh, someone's ringing the doorbell. Now the images are getting even more complicated. So hopefully it's still followable. So an extension to the simple method. So like I just said, instead of comparing just to that given first frame template, we can also compare to the predictions in the previous frame. So in this way, we're able to find the object that it wants us to find, but we're able to use the fact that we found it in the previous frame to ensure temporal consistency. And so we make a bunch of different versions of our method. So one version is the version that I talked about before, where it doesn't use any temporal consistency and it just redetects the first frame object. A second version is basically where it does this. So it knows what it predicted as the best object in the previous frame, and it runs the redetection head twice. So you can see the first time it runs the redetection head from the first frame template, and then it gets a bunch of boxes that it thinks should be the first frame. But you also have the boxes in the previous frame that you've already guessed are the boxes in the first frame. So maybe you were a little bit unsure in the previous frame and you guessed 2 boxes. Well, we want to be able to take that into account here. We don't want to just force it to say, okay, you were right in the previous frame because you might have not been. So in this case, you might have 2. You might have, okay, in this case, there's 3 previous frame boxes and 2 current frame boxes. And so we want to take into account the spatio-temporal consistency. So basically, in order to take that into account, we only make comparisons between boxes that have are similar enough in time, so it might move only slightly in time. And so then we can run this redetection head again, but instead of comparing the patches to the first frame template, we can compare them to the previous frame objects, and we can see the similarity. So what this means is that we can build up, basically what we can build up is we can build up the likelihood that each proposal, I should have put a slide on this with nice pictures, but I don't have it. So we can build up basically what I would call a unary term. So a score for each proposal, how likely it is to be the object that you actually want to track. But you can also build up pairwise terms between pairs of frames. So then you have the connections between all of the proposals in the current frame and the next frame, and you can build up the similarity terms between those and say, okay, well, if it's this object, then it's most likely to be this object in the next frame. So in the simplest version of using this, you just simply can take these unary terms, take these pairwise terms, and then say, just have some weighted average of the score of what you want to like, tune some parameters, and then you give an output for that. So that's a version that looks like that is what we call our short-term tracking version. But that's not the final version that we propose in this method. We want to do better. So that leads us onto the next thing that we want to propose. And we call it, and now it's getting even a bit more complicated, but it's okay. We call this the tracklet dynamic programming algorithm. So the idea is we have this history over the whole video where we have all of the pairwise terms between all of the proposals in each contiguous frame. And you want to use this history in order to select the best tracking result in the current frame. And so the trick here is that, normally in tracking at each frame, you just select what is the best prediction. But, and you might use the history of what you thought was the best prediction. But we wanted to change this, and we wanted to actually be able to change the past if the new evidence says that the past we thought was there was wrong. So in each frame, we don't want to just predict the best prediction, but we want to also predict the best history. So how do we do this? Well, we use dynamic programming, and it makes it still run fast and online. And the reason why this is super necessary, and we'll show it in ablations later, is that it allows, if something goes out of view and comes back, then it allows the object to just it allows the tracker to detect that really well. Or if there's incorrect predictions, it allows the tracker to ignore that really well and therefore perform really well in long-term tracking. So, okay, so my diagram doesn't really show how this works, but I think there's another slide. Yes, okay. So how does this work? So we maintain what we call tracklets. So tracklet is like a short tracking result. So you have detections, they're connected, they're contiguous in time, but they don't necessarily span the whole video. So it might just be 5 frames, it might be 6 frames. And so what we want to do is it's kind of a hierarchical approach, where first we build tracklets, and then we link tracklets. So the idea is to do the easy decisions first and fix them. So we build tracklets basically by taking, like we talked about before, the detections in the previous frame and the detections in the current frame. And if the redetector says these are super likely to be the same thing, and nothing else is likely, there's no conflicts, then we'll say that's correct. If, however, it's not sure and there's potentially conflicts, then we'll say, okay, we're not going to make that decision now. We'll save that decision for later, and we won't connect those things. So we either connect them or we don't connect them. And if we connect boxes, they become tracklets. So we can connect boxes in 2 frames, the next frame add another box, and the next frame add another box, and then you might get a tracklet that's 10 boxes long. And then at a second stage, what we do is we merge these tracklets into a long-term history of this object. So let's go through it as I've written it out. So basically, we have all of the, so in a new frame, so now we want to detect what's happening in a new frame, right? So we have all of the tracklets that we calculated in the previous frame. So we run the redetection head using the first frame template, and that gives us all of the boxes that could be the object that we want to track. So then we run the redetection again, but instead of the reference being the first frame, it's the previous frame. So now we get these pairwise scores between the previous frame and the current frame. So then we use these scores and the spatial distances. So when you have 2 frames that are contiguous, the spatial distance is relevant now because spatio-temporal persistency means that the object shouldn't have moved very far. To extend the tracklets, like I said, or either to start new tracklets if this detection shouldn't belong to any previous tracklet. And then basically we just simply run a dynamic programming algorithm which takes into account the unary terms for all of the different detections in every tracklet, as well as the pairwise terms between tracklets. So actually we run the redetection head again between the last frame of every tracklet and the first frame of every tracklet, such that even when there's a longer gap, we can get the similarity between those tracklet terms. And then, I'm not sure I don't think I have another slide on it. And then basically at each time step, when a tracklet's been updated, when the unary term's been updated, you then just select the sequence of tracklets based on this dynamic programming to give you the best sequence, which gives you the best current detection. And in each new time step, this best previous sequence might change. So then you can update what happens over time. So that works really well. So that's what I have to say about that. There's some other extensions that we use to make it work really well. So this is what I was talking about before when I talked about the fact that relying on the RPN is potentially problematic because it relies on it being able to detect objects that weren't necessarily trained on. So we ran a test to see if this was the case. And so if you look at the blue solid line in this graph, then these are objects that are not on COCO. So the RPN was never trained on anything that looks like these objects. And well, surprisingly, it does work really well if you use 10,000 proposals. So if you put 10,000 potential boxes in, it manages to correctly find enough. Well, if you're required to take 10,000 boxes out, then one of them is usually good enough. By default, we use the default also for the detector is 1,000, and it works pretty poorly. It's now only at 70%. And we also wanted to make a fast version that only took 100 proposals, and there it's really bad. In contrast, you can see the results for things that are in COCO are much better. They're up over 90% for all of the range. So we weren't very happy with those results. We wanted to track objects, any objects, random objects that weren't in COCO, unknown objects, because you're given this first frame, so you should be able to track it. So the solution to this problem was actually really easy. Basically, all we had to do was add the previous final predictions into the set of proposals, like concatenate these proposals to the proposals that came out of the RPN every time step before feeding this into our redetection head. So what this means is because you're given this first frame box in the ground truth, then in the second frame, after that first frame, you have as a proposal the box that was in the previous frame where that first frame ground truth template is. And so that's actually usually pretty close to the thing that you want to track because video is usually high frame rate, right? So things don't move too much. And by simply doing this, basically we solved this problem of unknown objects. So we didn't just like I said before, we didn't just put in the one best prediction of each time step, but we put in all of the final redetection predictions. So in that case, it was actually up to 100. So usually it's much less. Usually it's like, maybe it might predict 2 or 3 boxes that are likely to be actually the object, but potentially up to 100 boxes, in addition to however many RPN proposals we have. And yeah, you can see that even for known objects in COCO, this improves the score a lot, from 93 to 97. And for unknown objects, it improves basically up to over 90 from before it being completely useless. So this was a great trick that made it work really well. And I've shown an example because a lot of the things that are asked to track are parts of objects. So like just the head of a person or just the wheel of a car. And these things are definitely not in COCO, and these are the things that it's failing on. So the example here is of a wheel. It works really well. Yeah, especially many of these data sets, heads are a common thing to track. I think we'll see some example of head tracking later. Yeah, so this trick worked really well. So what other tricks? So here's another trick. So trick, extension, methodology, whatever you want to call it. Hard example mining. So this basically is at training. So like I talked about before, how did we train this thing? Well, we just trained it on 2 images, and the positive was the correct one, and the negative was everything else in the image. Well, when you sample 2 images from the same video, most of the rest of the image probably doesn't look at all like the object that you want to track. So it's not a very hard negative. And therefore not that useful for training. Because your tracker will just learn to do that really well. But then you apply it to a test case where you have 2 objects that are really similar, and it will fail. It will get confused. So what's the solution? The solution was, or part of the solution, you'll see that there's still some problems with this. But part of the solution was to explicitly train the method on hard examples. So what we did is, for every object that we wanted to train it on, so at training time, we actually mined hard examples from other videos. And we added these hard example patches in as negatives during training. So we pre-computed these and added these in. So I think I have another slide saying exactly how we did that. So yeah, here's some examples. So here you have this lizard. That's the object that we use as a positive. So we want to say that lizard and the same lizard in different frames are positive. What are some negatives? So these are some negatives from different videos. So we want to say, nope, it's not the same as these ones. And the same for this person over here. So then we have different people from different videos. These are extracted automatically. We didn't annotate these. We extracted them automatically. So how did we do that? Well, we use the embedding network, so a network that takes in an image patch and outputs an embedding, and we trained this with a triplet loss, basically such that the embedding for 2 objects from the same video, from like the same object over time, should be close together, and 2 objects that are different should be far apart. So once we had, then we extracted this embedding vector from this trained network for all of the boxes and all of our video data sets. And we took this embedding vector and stored it for every single box and put it into an efficient indexing structure so we could easily search over these embeddings via just the nearest neighbor query. And then at training time, we sampled our 2 images from the same video, so it's reference and target. And then from the boxes that you wanted to track, we extracted an embedding. And we've already pre-computed it for everything. So we took this embedding, searched for other videos that had a similar embedding, and added those patches in, also just with their pre-computed ROI-aligned features into the training as additional negative examples. And this improved the results a lot. We'll see some results of how that improved later. So I think this is the final extension, is that we also wanted this thing to do segmentation tracking. I talked about at the start. So basically the solution was just to add another network that took the final detection result, the final box, and output a segmentation. So it's kind of a separate network. It's kind of just does it. It takes an image, we concatenate the box that we predicted to the image as a 4th channel, and then it is fully convolutional network that outputs a segmentation mask. So now let's talk about some results. And we're going to start with some ablations of these extensions and see how things work. So to start off with, so the whole method runs at around 5 FPS, and it gets some scores on three data sets that are commonly used. Cool. So now let's start with the hard example mining. Well, the hard example mining helps. So in this case, it improves the results by 1.7%, I think, and in this case, 1.6, and here a little bit. So that hard example mining helps. We'll see in the next tabulation where it helps the most. And then I told you we had 3 versions of the method. So the argmax version is the very first version I talked about with no temporal consistency, where we just take the first template and then redetect the object in each frame independently. And the short-term version is the version where we just take the previous detection and then combine the scores from the previous detection and the template detection to get the result. So then we have some temporal consistency in there, but it's kind of hard temporal consistency. It's kind of like we trust the previous prediction and we want to be similar to it. And then our final Siam R-CNN result is with this tracklet dynamic programming algorithm that's able to update its past. And so now we have kind of what we call a soft temporal consistency, and that it's able to use the past information, but it's not super heavily reliant on it. And so you can see that this tracklet dynamic programming algorithm helps a lot. It improves over the argmax by 7% here. We'll just look at one. You can look at the other numbers while I talk. And it also improves 3% over this hard temporal consistency just from the short-term algorithm. Now, interestingly, this LASSOT and the LTB, these are long-term tracking data sets. So in this case, the object can disappear and come back. And this was one of the cases that we wanted to really improve. So when you do the short-term tracking algorithm, when you have this kind of hard constraint on the temporal consistency, and the object disappears and comes back, well, in those frames where it's disappeared, you're still predicting something. So these benchmarks require you to predict something, but usually score it low. And anyway, you're probably predicting something. So then when it comes back, you're probably going to continue to predict whatever you're predicting when it was gone, rather than the correct thing you want to predict after it comes back. And we see that happening here with our short-term algorithm that performs quite poorly, much more poorly than completely ignoring temporal consistency and just independently predicting per frame. So that's really interesting. Whereas for our final method with the tracklet dynamic programming algorithm, we get to see the benefit of both. So we get to have the temporal consistency, so it improves the result a lot in like the short-term tracking data sets, but we also get to have this in a soft way that we're able to ignore this temporal consistency if we want, if that's the best decision. And so when the object comes back from not being in the scene anymore, we're able to still successfully track, and in fact, even better than without the temporal consistency. So here's a big table. Now, I've been told big tables don't belong in slides, so don't try and read it all. I'm going to point out some stuff. So let's start again. So with the same ablations, let's start with the hard example mining. So overall, it improves 1.7%. Now for the other category, and I guess I should use my mouse to point rather than my finger, because you can't see my finger. So overall, this helps by 1.7%. So this is on the OTD data set. And we have different categories here. So this helps the most when there's background clutter. So this makes sense. Then you have by clutter, it means other similar objects in the background. So this hard example mining that's trained specifically to solve this helps quite a lot. And it also helps quite a lot putting low resolution images. So in low resolution, everything kind of looks similar. So training things specifically in this case, it helps really a lot. And then at the bottom, we have the 2 previous state-of-the-art methods that were the best before our method. And you can see that, you know, we have an improvement of both of them, but this is particularly strong for low resolution images. And so we propose that part of that is because of this hard example mining that's able to really tell the difference between things that are even quite similar in low resolution. Most things are. So the second thing that I want to point out is the effect of the different ways we did temporal consistency. So the same as what I talked about before is overall, the argmax version performs much poorly. the short term it helps, but the algorithm with the tracklet dynamic programming algorithm is the best. But the most interesting category here is out of view, OV. So this is when the object goes out of view and comes back, for example. So then you can see that again, like we saw before, the ordering between the argmax and the short term is switched. The short term algorithm is very poor in this case compared to the overall algorithm. And even compared to the argmax, our tracklet dynamic programming algorithm is much better in that case. And interestingly, you can also see that for this out of view, our method is much stronger than the previous state of the art. So this is really a place where our algorithm, because of this tracklet dynamic programming approach, really improves over previous methods. Cool. So we weren't happy with 5 FPS. We wanted to make it faster. Other trackers ran faster, so we wanted ours to be good and fast. So we played around with ways to make it faster. So the first way is by using a smaller backbone. So the original was a ResNet 101. So let's run it on a ResNet 50. Okay, it gets slightly faster. Most of the computation is in the redetection head, not the backbone, so it doesn't get too much faster. You can see that the results get a little bit worse, but it's still quite good. What if we run it on smaller images, so half resolution images? Well, then it gets even faster, and surprisingly, the results don't go down that much because, like we saw, it's the method's quite good at low resolution images. So in this case, actually, we get better result with half resolution images. On a plot that we saw before, we saw basically with different numbers of region of interest being put into the redetection head from the RPN. And so we played around with, by default, we had 1,000. And so if we put less proposals into this redetection head, then it has to do less computation, right? So with 100, it's 10 times less. So that makes things faster again, but work, you know, a little bit worse, except in some data sets. I mean, everything's a bit different. And then obviously you can put all of these three things together, and the method still works pretty well. So these numbers actually compare to the previous state of the art pretty closely, especially on these two long-term tracking data sets. It's still state of the art. And yeah, we can get it to run up to 15 frames per second. Good. Oh, 1 second, I did something. Where did it go? Here we go. Okay, good. So another point that I want to bring up is that many previous works kind of tune their hyperparameters per data set. And while this seems obviously bad practice, it has been surprisingly common in the visual object tracking community. So this is I'll just lay out, this is, I would say, very bad practice. People shouldn't do this. So our Siam R-CNN is trained on those 4 data sets that we saw before. It's the hyperparameters are tuned on a different data set, so on the Davis 17 training set, which is not used for actually training the method, and it's also not used for any evaluation. And these parameters, these hyperparameters, are used on all of the different benchmarks, which is surprisingly not how many trackers have done it before. So now another big table that I've been told not to put in, but it kind of shows something interesting. So first, there's a lot of tracking benchmarks. So in this case, there's 10 short-term. Oh,
sorry,
yeah.
Why not to put in?
Big tables are really hard to pass in a presentation. So if I had more time and was more prepared, I probably would have liked to have turned this into a series of nice graphs that just very simply visually showed the results that I was trying to show people. Whereas
Anyway,
if people look at, say this again?
This works as well. We get to know so much.
Yeah. Okay, well, as long as I go through and explain it slowly, because I don't want people to try and extract the information from this by themselves, because it's just too much. So at the top, we have our method and our scores in this first row here. And we have a bunch of different data sets. So there's 10 short-term tracking data sets, and there's 4 long-term tracking data sets. So then this table is actually much longer. There's a ... I have it for many more conferences, but I wanted to present all of the results from all of the methods from the recent conferences. And so the first thing you can see is that most methods kind of pick and choose which data sets they evaluate on. No paper is evaluated on as many data sets as us. I guess there's a good reason. It's that it takes a lot of time to do this, but I think it's worth it to get a good, consistent meaningful evaluation. The second thing to note is that some of the numbers are colored. So I've used, RGB as a color scheme. So the best method for every database is in red, the second best in green, and the third best in blue. And so the first thing that stands out is that our method is red, is the best method on 6 of the short-term tracking datasets and all of the long-term tracking datasets. And second best on some more, and third best on another one. And there's a few methods that are better on some datasets. It doesn't work perfectly everywhere, but it works pretty good, pretty promising results. The second thing that's worth pointing out is this number above it. So basically the question is, what's the difference between our method and whatever other method was the best before our method? So you can see for short-term tracking, for many datasets, for some datasets, we get a huge improvement. So 7.2% in tracking net, 3.8% in GOT10K. And it's a little bit worse than some state-of-the-art methods in other datasets. For long-term tracking, over the board, the improvements that we made have had a huge effect, especially because of this tracklet dynamic programming algorithm. So up to 10% improvement in score over the previous state-of-the-art, and consistently large, over about 4% or more over all 4 long-term tracking datasets. Yeah, so in terms of most of these methods are kind of based on a Siam RPN kind of architecture. You can see the Siam RPN++ here. So at the time when we first made this table, the results from ICCV weren't out, and so that was the best method across a lot of things. And then we updated it to have the ICCV 2019 results, in which case DIMP came out at the best. Yeah, okay. So then, like I said before, we wanted to make this through video object segmentation. So we wanted to compare it to video object segmentation methods. So these are the results on the YouTube-VOS video object segmentation data benchmark. So we wanted to kind of evaluate the score against the time it takes for a method to run, because a lot of the methods, e.g. my previous method here, are very slow. So this kind of shows something interesting. And we also wanted to differentiate between different methods, because our method doesn't actually take into account the first frame mask, the actual mask when tracking. It just takes into account the box. So in some ways it has a disadvantage compared to many of these other methods. And so we wanted to highlight that. So there's 3 dots that are our method. This one, and this one. So this red one in the middle, this red circle, is the default method. Just everything default. And you can see that when we first ran this experiment, it was state-of-the-art results. Since then, this STM-VOS came out and is better. So that was already published by the time we published this, because it took a little while to publish it. But still, even with everything, it's still the second best method for video object segmentation. And the results get slightly worse, but not too much worse, when you run the fastest method. So the low resolution and the ResNet 50 and less proposals. It doesn't go down that much, but it gets much faster. And then we have a slower method where we fine tune just the segmentation. So in my previous work, is this one, PreMVOS, which we've just got slightly better than in this method here, was much slower, and it showed that fine tuning results, especially the segmentation on that first frame segmentation that you're given, can improve the results. So again, we showed that we can get slightly better results using our tracker and fine-tuned segmentation network. So another interesting question. So the results are good compared to previous methods. They're really good, especially long-term tracking. Now, a question that we wanted to ask is it good just because of the data? And the answer is no. So we trained on 4 video data sets, these ones. They're reasonably, they're reasonably large in terms of number of frames, because 9K video ends up being a lot of frames, but it's not super large. 18K video, kind of 18K different objects. It's large in terms of processing it, but in terms of actual diversity, it's medium, I'd say. And now the previous state-of-the-art methods ended up training on more data, even though they train on different data, it ends up being more. So we used COCO pre-training, but so did all of the other methods. And so, yeah, we just wanted to investigate that. Is the method good just because the data we trained it on? Well, no, the previous method said it's better than even using more data. So I'm coming slowly to the end, but I don't know how long I've talked for. In fact, I have no idea, but that's okay. So let's start with, let's finish with some nice pictures. So it works on random objects, whatever this little toy is, it works really well. It works with large camera motion and large blur. It works when there's distracted objects like different bottles turning up and things happening. So, however, it doesn't always work. So still distracted objects, even though we try to deal with them in a number of different ways, are a problem. So in this first video, you can see it works pretty well, and it skips to a different person, and it skips. I mean, it's kind of hard to tell exactly the situation. In the second video, there's a bunch of birds that look identical, and it gets very confused about what's what. And in this third video of people running, you can see it's tracking that person. It's not supposed to. It's supposed to track that person at the very front. So it's just actually completely failed here. Because the people ended up looking very similar. So how about long-term tracking? Well, on this left, you can see this example where the ball goes out of frame every time. So in this case, you're actually supposed to predict the box for every frame, even when the object isn't there. You're supposed to score it. So we've visualized this by making the box red and very obvious if the score's high and black if the score's low. So when the object goes out of frame, you can sometimes see a box, but it's black, and that's what's supposed to happen. The results are very good. This is the sequence in which the results are the best compared to previous methods by far. So previous methods really struggle when that object comes out of frame and comes back, and ours works really well. And then again, you can see tracking a lizard with some kind of cat or dog or something jumping around. The lizard's running around. And this, yeah, works pretty well. But again, it doesn't always work. So in this case, you have this person in blue, and at some point it gets confused and ends up tracking the hand of the person, which is also dressed in blue. So, you know, overall the results are very good, but they're not perfect. So there's lots of things to work on. And in this case over here, well, things are very confusing. And when it's gone, it's quite confident that this letter is a bird. I'm not sure it looks like a bird, but the algorithm thinks it looks like a bird. So how about video object segmentation? Well, again, in many cases, the results look pretty good, without a doubt, but in other cases, less so. So in this one, it's kind of, at some point, tracked the bike as both objects and got very confused, and the segmentation is completely screwed up. In this middle one at the bottom, again, things are very confused. The results are bad. And then again, here in this right one, it tracks people well at the start, but as soon as there's this big occlusion, things get very confused. Now, what we have to realize when we're looking at these results is that it's a little bit different than the results for the long-term tracking. And the reason is, for the long-term tracking, you can just simply predict something with a low score, and then it kind of ends up as a black visualization and things look good. Whereas here we have no visualization of the confidence of the predictions. So things look really bad, and they are really bad because the evaluation measure doesn't care about your confidence in this case. But it's not necessarily that the method is completely failing, it's just predicting something in every frame. And that something is sometimes a bit rubbish. But it is also completely failing in some cases too, especially at the bottom here. This sequence is really hard. It shouldn't be, but it is. So I just wanted to, before I finish, just very quickly go over some other recent work in case people are interested. So the paper that I've been talking about at CVPR 2020 was this visual object tracking given the first frame. Mostly I've been working on a slightly different but very related application area of tracking objects when the first frame isn't given. So you have to just detect objects and align them consistency over time. But you're not given what objects to track. Instead, you're given what class of objects to track. So in the images you see, you need to track everything that's a car and a person. So there's different challenges for tracking because you don't know exactly what you have to track. You have to find that. That's very hard. In many cases, in certain ways, things are less hard because you can just focus on getting good trackers for cars and people, and you don't have to worry about tracking any kind of random thing that somebody could draw a box around and tell you to track. So at CVPR 19, we made a data set for doing this multi-object tracking along with segmentation. So segmentation on video is something I'm super excited about, and a method to solve that. So check that out if you're interested. At ICRA 2020, what we wanted to do is we wanted to kind of put the 3D into the tracking equation. So basically, we had this paper track to reconstruct the track, and we tracked objects as tracklets, like I talked about before. And then using those tracklets created 3D reconstructions of the objects, as you can see down here, or in the images of the right, on the right, you can see the object as it moves through time, and then the reconstruction as a combination. And then use these reconstructions in order to use this 3D model and 3D motion in order to get better tracking. And then a final work that I wanted to just quickly mention is actually something that I only uploaded on arXiv yesterday. So it's super new. So this is a paper that has just been accepted into the International Journal of Computer Vision. And basically, one of the big problems of multi-object tracking is that the evaluation metrics, to put it maybe not so lightly, have sucked. So previously, people have been evaluating methods mostly with the MOTA metric or the IDF1 metric, which just briefly, basically MOTA kind of only measures detection, and IDF1 kind of only measures association over time and ignores detection. And so we made a metric called HOTA, which is explicitly a combination of a detection score and an association score, such that, as detection improves, the detection score increases, which, as you can see, someone's just joining now. As you can see, aligns with MOTA, but as the association improves in the opposite direction, the association score improves, which aligns with IDF1, and as a combination of a detection association score, we have a HOTA score. So if you're working on multi-object tracking, or you're interested in it, definitely check that out. There's another metric called track MAP, which I don't like at all, which would score just 0% for all of the cases here. But that was just a brief little tidbit into other things I'm working on. Why can't I go to the next slide? Here we go. I don't know how long I've talked. Wait, here's my phone.
No, that's okay. That's completely okay. We have lots of time. So proceeding with questions. If anyone in audience has a question, you can please go ahead and unmute yourself. Else I'll start launching my set of questions. Okay, so I'll start. If anyone else has to ask, you can intervene in between. First question was what you covered in the last part of the talk. That was based on how do you compare Rollo with your single object detection, single motion tracking thing.
So sorry, say that again.
How do you compare your work on Siam R-CNN with Rollo, recurrent YOLO?
Okay, I don't actually know this recurrent YOLO method. So I don't know. I'm assuming it's some kind of tracking method.
Yeah, it was the approach was a little bit similar on taking the previous or prior feedback into consideration. So that's the question.
Okay. A lot of methods do this, so it's pretty common to do this. I'd say that from what we've put together, from what I've talked about today, none of the kind of just core concepts necessarily are super novel. Like, people have been thinking about this for ages and trying to get it to work. But there's still a lot of work in putting things together in a way that works really well. So I mean, in this case, to sum up what the paper was about, there's basically three main contributions. One is like two-stage detection for tracking, so two-stage trackers. One is this tracklet dynamic programming algorithm, so like soft association and being able to update the histories. And the third is this hard example mining. And so all three of those things help. We show that all three of those things help. Now, all three of those things are like novel things, but just kind of the general idea of using pass frames or redetection, or lots of general ideas people have been working on and are present in many different papers.
Sure. The next thing is, what are your views on using graph neural networks for tracking?
Yeah, I love graph neural networks. I'm working on something at the moment, which hopefully has some component of graph neural networks, and hopefully ends up working really well. Oh, somebody else at the door. My views are that I think graph neural networks are a very natural way to kind of encode the tracking problem, because traditionally, as you've seen with many, as has been the case with many kind of tracking by detection methods, you kind of have your detections and you set up a graph over those detections and you do some kind of inference on that graph to get the final output. Graph neural networks are kind of a natural way to do that inference. There's a great paper by Guillaume and Laura Lial Teixeira about using I think it's called learning a neural object tracker or something, where they use graph neural networks.
One question, Jonathan. What were the reviewer comments like? Anything specific that you can remember for this paper?
What were the reviewer comments like? So we actually submitted it twice. So the first submission was to ICCV 2019, where it got rejected. The main reason it got rejected was not because of the method. The method was very good, but because of the paper writing. So it was very rushed. The kind of storyline wasn't as clear, but it was really good to take that rejection and to take our time and submit it again to CVPR 2020, where it got accepted. And at that point, so we got 3 weak accepts. So all of the reviewers wanted to accept the paper. None of them loved it, which is, you know, fair. Yeah, they all liked it. They all gave us constructive criticism. So we made a number of improvements after their feedback to the final version of the paper. But there was a big difference between the ICCV submission and the CVPR submission. So just really taking our time, doing it right. And like was mentioned at the very start of the talk, that somebody found the paper really nice to read. We really just wanted to make sure that that was the case and have the writing really good, because that was definitely not the case in the very first version of the paper.
Right.
Go ahead, Shambhavi, thanks.
Yeah, so next question would be, any existing solutions for center track and chain tracker?
Existing solutions for what, sorry?
Center track and chain tracker.
So center track is sorry, I'm not 100% sure what this is talking about. Center track is this method where they track okay, that's something to do with multi-object tracking, right?
Right.
Okay, and what is the second one? Change tracker. I don't know if I know it either.
Like chain tracker would be continuing the multiple objects together.
Okay. I'm not exactly sure what the question is asking, because maybe it's relating to some related work that I'm not 100%.
So no, I got these questions on emails from people who could not join together and wanted to watch the recording on YouTube and wanted their questions to be asked.
Maybe Shambhavi, you can just pull that up on your computer so that Jonathan knows what you're talking about.
What's like chain tracker?
Yes. If there is any more info, you can just pull that up on your PC. Yeah. Meanwhile, Jonathan, when you had 2 or more objects, I had one question before that. What do you term as an extension? Because I haven't seen that in other papers. So what does a extension qualify as compared to?
You mean when I use the word extension in my talk?
Yeah.
So I mean, this was just something that I just wrote for the talk to kind of try and organize my thoughts for the talk. I kind of, wanted to just present it as like, okay, here's the core of it, like basically this 2-stage detector, here's the core, and then here's all of the additional things. I think kind of framing things as a core and an extension makes sense for things to be understood. At the end of the day, all of the extensions are included in what we would call our method, So our method includes the core plus all the extensions. Okay. Yeah, just the framing for talking about it.
Yeah. Because I haven't seen anybody use that term, extension. Yeah. Yeah, probably, Jonathan, it's in the chat. You're the one that is chaining paired attentive results.
Oh, my screen share died. Okay. In the chat.
Others, if you have any, Others, if you have any questions, you can just unmute yourself and go ahead.
Yeah, I'm not sure I can talk about this change tracker now without looking into it. I haven't seen it before.
It's fine. Yeah. Other question, Chama, you can go with the next question, please.
So,
I had a question.
To the topic.
Yeah. Go ahead.
I wanted to ask, when you do the dynamic programming in Siam R-CNN, so suppose if you update like the past prediction, like does it act like when you evaluate the results, will you use the updated version of the past predictions, or is it online that okay, in that time set we just predicted that object and you're not going to change it? So like how is the evaluation done in that setting? Sorry, I'm
So,
kind of new to this.
well, evaluation is done online always, so it never uses future results for outputting something from the past. However, because that's a requirement for many of the benchmarks. So like the VOT benchmark or the OTB. So OTB, for example, stands for Online Tracking Benchmark, right? So the requirement is that the trackers run online, that you only see all the past frames and output your result. So in each time step, internally within the method, we basically are able to change the history, but that change is only able to affect the output at the current time step or the future time steps. It's because we've already output something for those past time steps. So the method is still online, but it's online in such a way that it's able to change its history in order to improve the current and future outputs.
Ah, thanks.
Yeah, go ahead, Shambhu. Yeah.
So yeah, not related to the topic, something of the topic now, more related to research. Say like I'm considering my case, I want to go for an MS from either RWTH Aachen or TUM. So and I am keen on joining research groups, the particular ones that I've shortlisted, and I want to just start away with research work as soon as I start my MS, so that I can, continue the work into PhD and everything. How do you suggest to go about? Is like we do the cold mailing stuff to the professors, like before
Yeah,
getting
no, so how would I suggest going about it? Don't email professors. Professors are notoriously bad at not responding to your email and ignoring you. And that's, so first approach the PhD students that are already in the group. You're gonna have a much higher chance of getting them. Secondly, do send emails, but maybe don't necessarily rely on that, because I think you might also be ignored by people sending emails there. So my recommendation would be, A, send an email, make sure you include lots of information. So typically people want to see like, maybe a brief blurb, whatever experience you have, maybe your grades if they're relevant, whatever's there, your goals, your thoughts, your wants, whatever, but also make it brief because people don't want to read forever. But the key is going to be, I think, to probably maybe not during Corona time, but to come into the office and say, hey, I sent you an email. What's your thoughts? Like, get back to me. Because I think emails are very easy to ignore.
Right. And that has to be done once I have already started my MS over there, not going.
So here's the thing anyway, that your MS, at least in Aachen, I don't know how it is in other places, is a separate thing to the research side. Right. So generally, you'll be doing a degree, you'll be doing courses, and you have to get admitted to that, something that has nothing to do with our lab or our professor. And then once you're admitted to that and into that, then we can say hire you as a research assistant, and you can do research with us and work on papers. But you have to already be a student. And yeah.
Two more questions. One thing is that as an undergrad, I and all my peers, we do face the similar confusion that should we expand our scope and try multiple things out, or just choose one thing and get into the depth of it, even if like the area is very narrow, opportunities get very narrowed down. What do you suggest? What shows more dedication?
It's a hard question because I think different people will have different answers to the question. I would say that more important question is, or a more important answer is to do what you love and to love doing what you do. So I would say that if you love doing X, you should do X. But if you love doing X and Y, then do X and Y.
Maybe
I think that doing anything for the kind of sake of maybe like looking good is the wrong reason to do something.
Right.
okay, maybe Jonathan, I can rephrase her question. So, you can correct me if I'm wrong. Let's say you are deep into problem A, and problem A is not giving you any returns. So, from the beginning, is it good to go with both problem A and B? Or let's say you're knee deep into problem A, but you know everything's already been done research-wise.
Okay.
So, yeah,
Yeah.
what do you do then? Yeah. Maybe
Again,
that's the
what I'm saying is just opinion, and other people might have different opinions.
Yeah.
But in answer to this question, my opinion is twofold. First, I think it's a good idea to work on one thing at a time, and I'm notoriously bad at this. I'm always doing multiple things, but I always regret it. So my opinion is do one thing at a time and focus all your energy on that, and you'll do it better. And in terms of if you're doing the one thing and it's not working, I think it's also a skill to know when to move on or when to keep pushing. And you know, sometimes you make a decision one way or another and you're wrong, but that's a learning experience. And if you, I think there's no correct answer as to what is the best thing to do. I think it depends on the situation, because sometimes pushing you're going to get somewhere awesome, and sometimes you're not, and you need to know when to move on. But
yeah,
Thank you so much. And
yeah, Jonathan. So, at what stage are you in? Are you wrapping up? Because I think you have done lots of work already. So, are you wrapping up your thesis, or at what stage are you in?
So I've been doing my PhD now for 2 years. So before that, I was doing a research assistant as a master's student, and did some more work then. I am currently not thinking about wrapping up. I enjoy being a PhD student. I enjoy what I do. So I want to keep doing it for a little while. At some point, due to life situations, I might want to do something else, be somewhere else. In which case, that will be the time to wrap up and find whatever the next thing is. But right at this second, that's not yet the time. So I have no plans of starting writing up my PhD thesis or finishing anytime soon. But I can imagine at some point in the future that will change.
Good. Do you guide any undergrad projects as well, or?
So I do guide some projects, but they're all with master students. So I don't have any bachelor students, but I have a number of master students that I'm working with.
Good.
one more question. So yeah, like when we are talking about a domain such as visual object tracking, it is a domain. But what if I personally want to work with GANs, anything to do with GANs, I'm obsessed with GANs. That is not the right approach, right? We should rather focus on a problem area, not the architecture.
No, not necessarily. I think a lot of good researchers also in architectures. Honestly, I think the more important, like I said before, is to do what excites you. If you love GANs and you want to work on GANs, then work on GANs. If that's going to bring you to work every day with a smile on your face and get excited about, you know, sitting at your computer and writing GAN code, then that's what you should do.
Thank you.
And one last thing, when you were testing on blurred images, had you deployed it on cell phones, or were you still using? I just wanted to know at what platform had you deployed it while you were testing it with?
No, so we didn't run it on a cell phone or anything. We just basically only tested it using our computers. We didn't run it live on anything. We just used the benchmarks. I mean, that's, I guess in some ways, it's nice that computer vision is so benchmark based so you can compare results, but B, it does sometimes end up being a little bit far away from the real world, right? Because just because your thing works fast and well and good on a benchmark doesn't mean it's going to work when you just like point it at something in the real world and hope it works.
Good. And I had two more questions. I believe you submit a lot going by the amount of work you're doing. So is there any pattern that you see from all reviewers about their expectation?
Yeah, I can give some feedback on that. So I would so a few things. It might come off a little bit unstructured, but I'll try. The first thing is to put in some effort into the writing of your paper. So, and by some I mean a lot. I think the way your paper is written, both in terms of like the content and the storyline, as well as in terms of like the actual writing, the clearness, it matters for reviewers. And it matters for people reading your work as well, which is actually more important than what the reviewers care about. A second point that I want to say is also that evaluation matters. So a lot of the complaints that reviewers might make is, your evaluation is unfair or incomplete, or you could evaluate on this benchmark. And while I agree that many of these comments often are unfair, like, you know, reviewers shouldn't expect you to evaluate on everything or compare to everything. In general, it helps. And if you're gonna, if you want your paper to not be rejected, it help, like, so that shouldn't be the goal really, but if you want, that's a good thing to have. If you have everything, if you compare to everything and have all the benchmarks and all the prior work, then the real reviewer in this case has nothing to complain about. And I think evaluation is important because one sees many papers where it seems like people are trying a little bit to kind of obfuscate, kind of change how the results look a little bit by maybe leaving something out or presenting things in a funny way. And usually this is a negative thing. Like, usually the reviewers see right through it. I mean, you get good reviewers and bad reviewers, but I also usually, you know, an area chair that makes a final decision can tell who's a good reviewer and a bad reviewer, and will take good reviewers' opinions into account more. And good reviewers are going to know if your storyline is a little bit, you know, dodgy. So it kind of just sums up as like, do the right thing and do all the things. Yeah, be thorough.
Yeah, and I assume you also review papers occasionally, because you are also reviewer, I guess. So in what papers do you shut down the paper? Or I believe you go through the paper once, browse through, and then you look at certain sections of the paper. Is that how you do?
Kind of. Reviewing takes a long time. So for CVPR 2020, where this work was published, oh, somebody wants to come in. For CVPR 2020, I reviewed 7 papers, and I think each one took me maybe about 5 hours of my time. So, I mean, when you read a paper, you can read it in much less than 5 hours. But kind of, yeah. So how do I do it? Just in a brief, kind of, maybe first I'll have a quick look at it in the same way as I would just a normal paper I'm looking at. Like, what is this about? Probably read the abstract, look at the pictures. That's kind of the first kind of approach. Like, get a feel for what it's about. You know, okay, this paper's about this. Then I'll just read through it top to bottom, but really slowly. So, like, I'll read every sentence and I'll write notes about every single time a thought pops into my head. And the notes are not structured. The notes are not meant for anyone to read. It's just notes. And usually it's lots of notes. So I just have a thought and I'll write it down. And that takes a long time, because it takes much longer than reading a paper. And it also means that you're reading it much more thoroughly. And then I will turn these notes into usually like an essay, I guess, right? Like a document in response to the reviewer. And the goal is actually to the author. The goal is actually to help the author in making the paper as good as possible. So you want to ask questions of what's happening, of what's not, like, you want to tell them, okay, I didn't understand this, maybe it could be made clearer, or like, what is actually happening here, I didn't understand, or stuff like that. And usually if I write a lot of notes, that ends up being a very long document. But hopefully whatever's in there is helpful. And, you know, sometimes the recommendation is accept, sometimes the recommendation is reject, but either way, kind of the goal for me is to be helpful to the author. And that takes a long time. So it, you know, I can review 2 papers in a day in a full-time day. So 7 papers is 3.5 days. It's like almost a work week to review for a conference.
One last question. How do you deal with papers which are not in your area of expertise? I assume you get those as well. Yeah.
For reviewing, yeah. So mostly I've had papers that are very related, but I have had some papers that are not super in my area of expertise. One comes to mind. What I did is I did my review process how I normally would do it. And then I asked a friend of mine that paper was very much in his area of expertise, just to give me his quick opinion. I didn't want him to spend 5 hours on it. But I wanted him I didn't want to give him any of my opinions to bias him, but I just wanted him to give me his quick opinion. And, you know, he looked at his paper and he told me X, Y, Z, you know, the review was negative, but he told me, you know, basically they're proposing X, Y, and Z, which is all things have been done before. Like he knew, like blah, 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 you know? He told me very quickly he knew some stuff, and that was what I thought, but I wasn't 100% confident on it. And then you just make that very clear in your review. It's like, hey, I'm not an expert in this. I'm an expert in this other field. It's kind of related. I have consulted this other guy that's an expert. I mean, you don't need to name names. And he agrees with me. These are the faults that I found with the paper. These are the faults that he found with the paper. We kind of concur on these facts. And in general, there's also just, yeah, I mean, some things are very domain specific and that it's very helpful to have domain knowledge, but in other cases, you can just kind of also evaluate you know, does the experiment make sense? Is the paper clearly written? Do you actually understand what they're doing from reading the paper? Do the experiments make sense? Like, will the experiments that they're doing actually validate what they're trying to show in the paper? Just stuff like that. You can kind of pick up.
Got it. So, Shambhavi, do you have any other question?
No, sir. All my questions got answered.
Yeah, one last question. I had one last question. Obviously, grad students from your group graduate and go to companies. So, those who go to industry, what is the expectation from them? Or, yeah, generally what happens in the interview? Do you have any idea about that? General idea?
For the interview process or
some PhD students, those who graduate, they obviously interview for some industries as well, companies.
Sure.
So generally, what are they being asked? Do you have any idea about it?
Yeah, sure. So I have a few friends that have interviewed. Personally, I haven't interviewed with any big tech companies myself, but usually you have a number of interviews, right? One is usually very research focused, and so it's just kind of talk about your own research. Usually by the time you're interviewing, if things are going kind of how they should be, you're already kind of interviewing with the people that you would potentially be working with, right? So they should know about kind of the research that they're doing and the research you were doing, and hopefully there's some kind of match, right? So usually there's a research interview and you really just dig into the research, tell them about what you're doing, tell them about what you want to do in the future, just, that kind of deal. And then there's this technical interviews that kind of the same thing as you would have to do if you were applying for a software engineering position after undergrad at Google, So can you code? Can you solve problems?
Okay. Great, Jonathan. Thank you. Thank you for your time. It was really insightful, very great work. And I think it was more of a journal, the amount of results you had put, I think it was more journal worthy, I felt. Because the amount, I think you took you presented so much results. I thought it was a good journal paper.
Thank you very much. I think we have to thank Paul, my co-author, the first author of the paper. He did a lot of that work. So
yeah.
I think I was a bit of the force behind, like, no, Paul, do it. It'll be better. So, but he was the one that ended up running a lot of those experiments. So
how much time did it took in total to finish this off?
We started writing it. Start of February 2019. We submitted it to ICCV middle of March. So we made the first version in 6 weeks. That was a bit rubbish because we took 6 weeks. Got rejected. And then the version we submitted to CVPR in middle November of that same year was basically the version that you see now. It was very polished. So we're talking the whole paper, start of February to middle of November is like 8.5 months. Although that wasn't necessarily the only things we were doing at that time. So we also organized a workshop. I also submitted some results to a couple of different video object segmentation challenges for ICCV.
Incredible work, Jonathan. Thank you. Thank you for your time. It was really beneficial.
Yeah, all the
thanks for
guidance
having me.
and questions, right?
Good. Well, thanks for having me. It's been good to be here. It's always good to have the opportunity to kind of put your work into context and tell people about it. So
yes. Yeah, and this was really needed in-depth explanation because it was really hard to follow when you just read the paper, when you're outside the area, obviously, but
Yeah.
you gave a very clear explanation. Thank you very much.
Awesome. Thank you.
Thank you. Yeah. See you then. Yeah.